Okay, students, so we are now in video lecture 30, and I will give you a schematic diagram of what happens at the boundary between, remember we talked about in the last class the amphibolite to granulite transition, and we did a detailed analysis of how hornblende breaks down and you produce 2-pyroxene plagioclase assemblages. So that's from the amphibolite to granulite, and from granulite and from granulite to eclogite, and from amphibolite to eclogite. These variations, I think it's a little vague. So what you do is essentially I give you a diagram which sort of is a very good framework to understand what the transformations are going, how the transformations are going on. So we'll draw the diagram and then we will go on discussing. So it's something like this. This is, of course, as you know, pressure and temperature. There are no scales here, but I will just draw the diagram. It'll take some time. Here. So we have A, B, C, D, E, F, and here we have something called G. These are different phase boundaries. So here, for example, this is this classical hornblende plus plagioclase plus quartz, this phase diagram here. And from there, if we go here, this is the eclogite phases. So we have clinopyroxene, garnet, and note here, I'm writing plus minus amphibole, plus minus quartz. That's the assemblage. And then we have garnet, clinopyroxene, plagioclase, plus minus hornblende, quartz. Then we have garnet, clinopyroxene, orthopyroxene, plagioclase, plus minus hornblende, plus minus quartz. And here you have orthopyroxene, clinopyroxene, plagioclase, plus minus hornblende, plus minus quartz. And we are left with this one, which is garnet, clinopyroxene, plagioclase, hornblende, and quartz. There is another line that comes in here, and I will give this a breaking line, where you have olivine, clinopyroxene, plagioclase, plus minus hornblende, plus minus quartz. And here you have olivine, this reaction line, plus quartz is equal to orthopyroxene. This assemblage here is called an eclogite. This here is amphibolite. The this is granulite. So this is a diagram which is quite helpful. I will just give you some important reactions here. Here, for example, you have olivine. You see, olivine, clinoperoxene, plagioclase, plus minus hornblende, plus minus quartz. As you move here, it's orthopyroxene, clinoperoxene, plagioclase, plus minus hornblende, plus minus quartz. It's very simple. You know, olivine plus quartz reacts to give you orthopyroxene. So if you take this olivine and replace it by this reaction, you get this reaction. Right? And these are this assemblage is here, which I give in dotted lines. In stipples. Oh, I have not given you this assemblage. You can well understand what this assemblage will be. It's not difficult. This G here, this is orthopyroxene, clinoperoxene, hornblende, plagioclase, quartz. This basically G of this assemblage. Now you see here, there is several important things that you should see. One is this part does not contain this one in blue stipples. Blue stipples. This area does not contain any garnet. This blue stippled area does not contain any garnet. This red stippled area contains this assemblage, garnet, clinoperoxene, plagioclase. This is very crucial. So here you have orthopyroxene, clinoperoxene, plagioclase, plus minus, you forget about it. Here you have olivine, clinoperoxene, plagioclase. So this is, if you move up pressure here, up pressure, this is olivine out. This is olivine out reaction. And if you look at this is all garnet in. Do you see that? This is all garnet in. But same here, this is also garnet in. So here you see that this assemblage here is essentially garnet in assemblage. Have you understood? Now you look at this part, all right up to this part. The whole thing is granulite fishes. Why? Because you have the characteristic assemblage orthopyroxene. But there is a difference between A and B. What is the difference? The difference is at A you don't get garnet. At B you start getting garnet. Right? Now this is important. Olivine out, as you move up pressure in the granulite fishes, you get garnet in, and suddenly you have this reaction. What is the characteristic of this reaction here? Here, for example, it's orthoperoxine out. Do you understand? This is orthoperoxine out. So you have 2-peroxine plagioclase assemblage, garnet comes in, then you have garnet, clinoperoxine, orthoperoxine assemblage. As you move out, orthoperoxine is now taken out, but you have garnet, clinoperoxine, plagioclase assemblage. Garnet, clinoperoxine, plagioclase assemblage. And when you go into this line, it's plagioclase out reaction. These are the critical case. If you go from low pressure granulites to eclogites, this is the direction of increasing pressure. So first what you will get is olivine bearing granulites, but this sometimes people don't call it granulites for the simple reason there is no orthoperoxine. But since this is an olivine plus quartz is equal to orthoperoxine reaction, so people keep this in the granulite pressures provisionally. But theoretically, since orthoperoxine is not stable, this is not in the granulite phases. But still, it's taken to be as some sort of a granulite phases assemblage. So you have olivine bearing granulites, orthoperoxine granulites, but no garnet till now. No garnet till now. As you move up pressure, garnet comes in. How we will see. And then as you move even more up pressure, orthoperoxine is exhausted. And as you move even higher pressure, plagioclase is exhausted out. So you have clinoperoxine, garnet, plus minus amphibole, plus minus quartz, which is a typical eclogite phase. So this happens where you have granulites. So what happens? People call this low temperature granulites, which is orthoperoxine bearing granulites. This is called intermediate pressure, where you get garnets, you call it intermediate pressure granulites. Or some people even refer to it, I think, this is called high pressure granulites. And this part below the garneting, this is called intermediate pressure granulites. So here, as you go up, low pressure granulites, olivine bearing, no orthoperoxine. Then olivine out reaction, and you have intermediate pressure granulites where you have orthoperoxine, but no garnet. As you go up pressure, then you have garneting, so you have high pressure granulites. Garneting means orthoperoxine is still not gone out. Orthoperoxine is still in the assemblage. Here you can see garnet, clinoperoxine, orthoperoxine, plagioclase. So this is still granulite phases, but this boundary here you see, here you don't see orthoperoxine. So this is this part. And this part, there is no plagioclase in mafic rocks. No plagioclase, no orthoperoxine, but both orthoperoxine and plagioclases are here. So this is the granulite phases. This is the garnet, clinoperoxine, plagioclase phases. And this is eclogite phases. If you come to the amphibolite phases, then amphibolite, Hodgman, plagioclase, quartz goes in to give you clinoperoxine, garnet, plagioclase, quartz. Remember, there is no orthoperoxine. There is no orthoperoxine on the amphibolite phases, or amphibolite phases to eclogite phases. There is no orthoperoxine coming in here, because orthoperoxine in means it will be a part of the granulite phases. And you have a phase field here, this phase field. If you see, you have Hodgman, plagioclase, quartz here. So as you move, you start getting garnet, clinoperoxine, plagioclase, and again you see garnet, clinoperoxine, plagioclase. So this red stippled area is a very peculiar area where you don't have orthopyroxene anywhere. You have garnet clinopyroxene assemblage. Some people call it sub-eclogite facies assemblage. Some call it sub-eclogite facies, or this is called the granulite eclogite transition zone. Granulite eclogite transition zone. In the last class, we were talking about this transformation. This is where we were taking a hornblende plus quartz and producing orthopyroxene, clinopyroxene, plagioclase. So we were talking about this transition, amphibolite to granulite facies transition across this boundary. Have you understood? So today, one of our main aims would be to go up pressure, this way, up pressure. So what will you do? Yes, last class we had hornblende plagioclase, and then we saw 2-pyroxene plagioclase assemblages. Now we take the 2-pyroxene plus plagioclase assemblages, plus minus hornblende plus minus quartz. These are not characteristics of granulite facies. Orthopyroxene is. And then we go up pressure and go into the eclogite facies. And we see what possible reactions may occur here. So remember, there are several things to be remembered. On the right hand side, you have granulite eclogite transition. On the left hand side, you have amphibolite eclogite transition. In between, you have amphibolite to granulite transition, except of this part where there is no granulite facies rock. But you have in this red zone a stippled area where you have garnet clinopyroxene assemblages, but you never have orthopyroxene assemblage. So that would make it granulite facies. So this is not a granulite facies assemblage. So this is intermediate pressure granulites, high pressure granulites, eclogites. What is the difference between intermediate pressure granulite and high pressure granulite? Garnet comes in. What is the boundary between high pressure granulites or garnet bearing granulites to garnet clinopyroxene? Orthopyroxene is taken out. What is the boundary between garnet clinopyroxene, plagioclase to garnet clinopyroxene? Is plagioclase is taken out. So essentially what we will be looking at, if we go up pressure, we should be looking at first garnet forming reactions, and then we should see how orthopyroxene is reacted out, and then we will see how plagioclase is reacted out. That is all what we expect if we are going this way and this way. Here it is much simpler. Hornblende will break down into clinopyroxene garnet. So again, you can take your Scherbakite molecule, because remember, these will be Scherbakite pergosite rich, as I discussed with you, and so this will break down to garnet clinopyroxene assemblage. You can do the reactions, you know the clinopyroxene formula. So this is the overall spectrum of what happens in the junction between amphibolite facies, granulite facies, and eclogite facies. So remember, how will you distinguish eclogite from garnet clinopyroxene subfacies? Eclogite will have no plagioclase. How will you distinguish this from high pressure granulites? Orthopyroxene should be present in high pressure granulites. This will not be present in high pressure. Orthopyroxene will not be there in this phase. So those are the transitions that we will be looking at. So today we will talk about some of the reactions that produce garnets and some of the reactions that takes out orthopyroxene, and some reactions that take out plagioclase. Now, before doing this, I think you have to remember this overall framework when you go. Now we are talking of garnet producing reactions. So we are going from intermediate pressure to high pressure garnets. So garnet absent granulites to garnet bearing granulites. That's what we are doing. And later on we will go into orthopyroxene out, plagioclase out reactions. Okay, so I erase this and let's write the reactions. Now, it's not very easy to do this, to study the garnets It's not very easy, but I will try to do it in a way that is you could possibly conceive it a little easier. And then I will tell you that the complication, that the easier things that I showed you were actually not right. Now, we take the assemblage OPX, CPX, Plagioclase. From this assemblage, which is a low pressure granulite, we will go into a domain where you produce garnet, so we produce high pressure garnet granulites. That's the basic theory. We are trying to do that. Now the composition of orthopyroxene is MgSiO3, FeSiO3, clinopyroxene CaMgSi2O6, CaFeSi2O6, and plagioclase is CaAl2Si2O8 and NaAlSi3O8. Of course, you have plus quartz. So this is the assemblage. So now if you look at the components, it will be CO, MgO, FeO. This should take, and you have SiO2 of course. So you have SiO2, CO, MgO and FeO. This takes into account orthopyroxene and clinopyroxene. But now for plagioclase, I have to take in Na2O. So this is now a 5-component system. So essentially, it's a 5-component system. Al2O3. Yeah, sorry, right. Al2O3. So this is essentially a 6-component system. Sorry, this is a 6-component system. But I will tell you after I finish this thing that we can take out SiO2 because SiO2 is there in all minerals, and so we can take out SiO2. There are theoretical reasons why you can take out SiO2. That I will do after I finish this, and we can do some chemographic analysis. So I will first take out SiO2 because SiO2 is present as a phase and as a component in all phases. So SiO2 we can consider as in excess. To make matters a little comfortable for us, and it's not right, but what we can do is club MgO and FeO. You see, this is 1, 2. It's not easy to draw 6 components on the diagram. There are ways to do it, that is what I will teach later. But for the moment, we take SiO2 as in excess, so we can forget about SiO2, and we can club MgO and FeO together in some sort of what you call, say, FeO star. What is FeO star? FeO star is FeO plus MgO, let us assume. So now what we have CaO, FeO star, remember it's a fictitious component. It takes in MgO plus FeO together, and then you have Na2O and Al2O3. These are the 4 components. But there is an important thing, and again I will tell this to you, explain this to you in a later class, in a later set of lectures. Al2O3 is present it's present in plagioclase if we neglect Na2O. Do you see why? Because Na2O occurs only in plagioclase. Na2O also occurs in clinopyroxene, as we will see soon, but that will be slightly complicated more. So what we have to do is CO, FeO, Na2O, Al2O3. If we omit Na2O because it's only there in plagioclase, so you have CO, FeO star and Al2O3. So this becomes a 3-component system which is easy to visualize. I will just give you an example. So say for example, say if this is CO, this is FeO star, this is Al2O3, and this is Na2O. This is a quadrilateral, this is a tetrahedron. Now you see on this, clinopyroxene will plot on the clinopyroxene and orthopyroxene will plot on the face CaOFeOl23. Garnet, which is CaFeL23, Mg2L2, they will also plot in the same face. But plagioclase will fall inside. Why? Because plagioclase should lie on CaONa2O-L23 face. So CaONa2O-L23 face is this face. This is the face where plagioclase will lie. But garnet, orthopyroxene and clinopyroxene, they will lie on this front face, CaOFeO star and L2. Have you understood? So if we are neglecting Na2O, then we are only taking the anorthite content of the plagioclase molecule. We are not considering the albite component of the plagioclase. Essentially, that is what is happening. So if we do this, I think is it clear? So this is the actual numbers, 6 component system. Since SiO2 is in excess, and if we club MgO and FeO together, because they have similar ionic radius, it's not right. But then we have 1, 2, 3, 4. And since if we consider our anorthite molecule in plagioclase only, we can omit Na2O and take our system to CaOFeO star L23. So we can handle it on a triangular diagram to see. It will be easier for us to see what the reactions are. So that is what we will do. This is highly simplified and it's not right. But to begin with, I think this is the best that you can do. So now I will, so I will draw the diagram. So this is a diagram where I have drawn it as CaO Al2O3 and then FeO star. Remember, FeO star is FeO plus MgO. That what is the problem with this? That I am clubbing FeMg distribution. I am completely neglecting it, which is completely wrong. But just for the sake of chemographic analysis, I am keeping this. So if I have to plot, and here you have plus SiO2 because that is in excess. Plus SiO2, that is in excess. So here if I plot, what is this position then for plotting? This plotting position then is for orthopyroxene. So let's say, since we have taken FeO star, let's say this is FeSiO3. This is, let's say this is FeSiO3. And then here this is CaO FeSiO3. So if I take FeSi2O6, which is the dioxide thing, then it should come at the middle point, it should plot. So this is CaFeSi2O6. This is hidden, but just remember Fe is star here and not actual Fe. Where will plagioclase plot? Anorthite molecule. Remember, albite we have taken out of calculation. So anorthite molecule is CaL2Si2O8, or CaO is to L2O3 is equal to 1:1 molar ratio. Right? So if we do that, these are all molar ratios, yes? So CaO and Al2O3, so Al2O3 should plot 1:1 Al2O3. So this is the position of anorthite. This is the position for anorthite. So we have plotted FeSiO3, we have plotted CaFeSi2O6, and we have plotted anorthite. Now we have to plot grossolar. So grossolar is Ca3Al2Si3O12. That means 3CaO is 2Al2O3. Sorry, CO is 2Al2O3 is 3:1. Is it not? 3CO is 2Al2O3 is 3:1. So there are 4 divisions. So 3CaO, it will be plotting, grossolar will be plotting here. Grossolar will be plotting here because there are 4. 1 CaO will be 3 by 4, 75%. This is 100% CaO. This is 0% CaO. So grossolar will be plotting here. Similarly, if we take almandine component, then you have to replace calcium by iron, which should make, instead of CO, you can write FeO, and then it will be 3:1. So again, if we divide it into 4 parts, so this will be almandine. So the garnet composition should lie on this line. The garnet composition should lie on this line. Because it's a solid solution between grossolar and almandine. Remember, your almandine also contains pyro. Your almandine also contains pyro. This is fictitious. Also contains pyro. So now, if your garnet lies on this line, then what are the possible reactions? This we have to find out. What are the possible reactions from crossing tie lines? So say for example, I take anorthite plus ferrocylite. Do you see that? This is anorthite plus ferrocylite should intersect this line. So I can write a reaction FeSiO3 plus CaAl2Si2O8, and this should give you a garnet. So that should be Fe3Al2Si3O12 plus Ca3Al2Si3O12. Right? Now, if we balance it, you see there are 2 aluminium and 2 aluminium. So, if I write 2 aluminium here, then I should, because I have to take in 3 calcium, so I write 3 anorthite. So, if I write 3 anorthite, then you see 3 Ca, and 3 Ca is balanced. Aluminium, 3 into 2 is 6 aluminium. Here you have 2 plus 2 into 2, 4 aluminium. That means I have to write 6 FeSiO8. Now let's see quartz. On the left hand side, you have silicon is 6. Silicon is 6 here. Silicon is 6 here. On the right hand side, silicon is 6 here and 3 here. So here we've equal 3 more SiO2, but that is simple. We can just take 3 SiO2. Do you understand? So if I take 3 CiO2, then this adds up to, once again, let me, 3 into 2, 6, 3, okay, plus 3 now for silicon. So this should be 12 and this should be 12. So your silicon is also balanced. Remember why I'm adding SiO2? Because SiO2 is in excess. So I complete the reaction, and so your oxygen, now you see your oxygen here. So oxygen is 6 into 3, left hand side, 18, left hand side, 24, so that should be 42, and on the right hand side, it should be 24 plus 12 plus 6, so that should be 42. So you have 3 silicon, so your silicon also is balanced. What is the reaction now? So this reaction here, anorthite plus ferrocyanide, gives you a garnet where almandine plus grossular ratio is in the proportion 2:1. Have you understood? So this is the low pressure granulite, this is the high pressure garnet granulite. So one of the ways in which garnet comes in is when orthopyroxene plus anorthite reacts to produce almandine grossular garnet. Remember, this is fictitious almandine. There is pyro inside here in some proportion. So this is reaction 1 here. So this is reaction 1 from the crossing tie lines here. This is one reaction. If I look at another reaction, then you can see here, this one, anorthite plus diopside, reacts with garnet. So this is our reaction 1, so I will write 1 here. And this is our reaction 2. So this is our reaction 2. What is reaction 2? Reaction 2 is CaFeSi2O6 plus CaAl2Si2O8 is equal to Fe3Al2Si3O12 plus Ca3Al2Si3O12. So you can see your calcium now. Calcium is 3. So calcium is 3. So if I give this as so if I give this as 3 and this is 3. So what happens? This will be 2 grossular here. Calcium is balanced, 3Ca plus 3Ca, and this is 6Ca. And your iron also becomes balanced because here you have 3 iron. I have 3 iron here. Aluminium, you can see 3 into 2, 6 aluminium. Here it's 2 aluminium plus 2 into 2, 4 aluminium. So aluminium is also balanced. And you will have, if you do it carefully, you will see you will have plus 3 SiO2. 3 SiO2. So this is clinopyroxene plus anorthite in plagioclase reacts to give you almandine plus grossular, but this time you see grossular, almandine is to grossular is 1:2. Here it was 2:1. So the effective garnet composition will be controlled by what is breaking down and in what proportion. Is there any other reaction? There is one more reaction. This reaction is a very classic reaction. I will draw this. This is, I think it is, you see that? This is reaction 3. I will put the 3 number here. What is it? OPX plus grossular. So that is OPX plus grossular is FeSiO3 plus grossular Ca3Al2Si3O12. And this gives you clinopyroxene, as you can see, diopside, CaFeSi2O6, plus almandine, Fe3Al2Si3O12. It is something like this. Now, how do I balance it? I take 4 iron, if I take, then I have 1 iron, and 3 iron, 4 irons are balanced. Aluminium is automatically balanced. No, I think there is a problem. Just one second. Okay. If I do this 3 grossular, so what will happen is I will have 3 iron and 3 iron, so that will be 6 iron. 6 FeSiO3, 6 iron, 6 iron, right? 3 calcium, 3 calcium, 1 aluminium, 1 aluminium, and silicon, if I look, it is 6 plus 3, that's 9, silicon on the left hand side, and the right hand side it's 6 plus 3, 9. Is that right? I think this is not the... This got an exchange reaction. No, I think I've got the reaction wrong. Just let me correct it. If I take, just one second, just one second. If I take FeSiO3 plus anorthite plus Ca-Al2Si2O8. Have you understood? FeSiO3 plus Ca-Al2Si2O8, and I get FeSi2O6, which is this one, plus aluminium, plus Fe3Al2Si3O12. Yes, now it is. Now it is okay. So this will be 1 iron, 3 iron. This is 4. This is 4 iron. So 1 iron plus 3 iron, 4 is balanced. Calcium is 1 here. Aluminium is 2 here. So if I look at silicon now, so silicon will be 4 plus 2, 6. That's silicon. And here it will be 2 plus 2, 4. So you will have plus 2 SiO2. That should be the reaction. So that should be the reaction, in which case oxygen should balance on either side. Oxygen should balance in either side. So here we have 4 into 3, 12 oxygen. Here it's 8 oxygen, so the total is 20 oxygen. And here you have CaFeSi2O6, 6 oxygen, plus 12 oxygen, plus 4 oxygen. No, what's this? 22 oxygen. Where am I going wrong? Silicon, have I done overdone? Silicon over. 4 silicon plus 2 silicon, 6 silicon. It should be a SiO2. It should be a SiO2. So this should be plus 2. And in which case this should be 22. So the reaction is 4 FeSiO3 plus an anorthite molecule gives dioxide plus garnet plus SiO2. That's the reaction. So what is this reaction? Ferrocylite plus anorthite gives you dioxide plus aluminium. Now the important point of this diagram is very simple. Why it's a very important reaction? This is the granulite facies assemblage, orthoperoxyl plagioclase. And this one is the assemblage of garnet clinopyroxene, which is the high pressure assemblage. So this essentially is the granulite facies assemblage, and this co-precipitates garnet, forms garnet, along with clinopyroxene, which is the garnet clinopyroxene subfacies of the diagram that I did. So these are some of the iron-bearing reactions. You remember I did it FeO star, I could have done it MgO also. So all this these are all all reactions that I've written are in the system CFMAS. That means calcium, iron magnesium club, aluminosilicate, aluminous, Al2O3 and the SiO2. So these are essentially the reactions that stabilize garnet in low pressure granulites, and you get garnet plus 2-pyroxene plus plagioclase, which is the high pressure granulite, can be formed through a reaction between orthopyroxene plagioclase, clinopyroxene plagioclase, and orthopyroxene plagioclase, but this time giving garnet plus clinopyroxene, which is the high pressure assemblage. And you can have also the magnesium end members. There are other reactions, but for the moment I think this would be the reactions that produce high pressure garnet granulites from low pressure garnet free granulites. So when you see granulite facies rocks without garnet, these are low pressure garnets. Okay, now that we have written this, there are other ways in which garnet forms, and you should know this. This does not necessarily become a part of this system, but there are other ways in which garnets also form from low pressure granulites to garnet bearing high pressure granulites. These involve opaque phases. So opaque phases normally are FeO, Fe2O3 and TiO2. So this is ilmenite, FeTiO3, which forms a solid solution with hematite. This is hematite and this is ilmenite. This forms a solid solution. And you have FeO, Fe2O3. If you take the middle part, this is Fe3O4 and this is magnetite. And then parallel to this here, you will get Fe2TiO4. This is ulvospinel. So magnetite, ulvospinel solid solution, hematite, ilmenite solid solution. So sometimes what happens, you can have such reactions as FeTiO3 plus Si2OH. You see that? Ilmenite plus anorthite, and now you can see it should give you Ca3Al2 Si3O12 plus Fe3Al2 Si3O12. But you have a problem here. What is the problem? Here you can, like before, you can write 3 calcium here, and you can write 3 calcium, 3 into 6, and 2 here, and 6 FeTiO. But the problem is, here you have titanium. So what happens? Here you get 6 TiO2, routinely. So this what happens is ilmenite plus anorthite in the plagioclase gives you garnet plus rutile. This is a very common texture where, for example, you get garnet coronas around ilmenite, and these contain rutile inclusions. So this is garnet and these are rutile inclusions. So these are cotectic growth of garnet and rutile. So if we balance this reaction, so on the left hand side you will have silicon is 3 into 2, 6, and on this side, do we need quartz? Let's see, iron is balanced. So on the left hand side you have 3 into 2, 6 silicon, and on the right hand side you have 3 silicon and 3 silicon, so you should have 3 SiO2 here. Just check for oxygen. Just check for oxygen. You should get it 6 into 3, 18 oxygen. Here it is 24 oxygen, and here it is 6 oxygen, 48. On the right hand side you have 12 plus 24 plus 12, that's 48. So you have ilmenite plus anorthite plus quartz gives you grossular plus ilmenite. This is another way that you get orthoperoxide, or that you get garnet. But this is not restricted, since it doesn't involve orthopyroxene. It is not only restricted to this, but it could be restricted to the amphibolite phases. This is not a reaction that is characteristic of granulite phases. This could also be a part of the amphibolite phases. Similarly, there can be other iron and member reactions. Say, for example, we have talked about ilmenite. If we take hematite, say for example, Fe2O3 plus CaAl2Si2O8 is equal to Ca3Al2Si3O12 plus 2Fe3Al2Si3O12, and this will be 3 and this will be 3, and you can see what it will be. Balanced silicon is 3 into 2 6, 3 into 2 6, and 2 6 plus 3 SiO2. So you have 3 silicon plus 6 silicon, 9 silicon, 3 silicon plus 6 silicon. If you go for oxygen, then you will see on the left hand side you have 9 oxygen, then you have 24 oxygen, then you have 6 oxygen, that is 39 oxygen, and on the right hand side you will have 12 plus 24, that is 36 oxygen. You will have an oxygen deficiency. This is because on this side it will be 3 by 2 O2. This is an oxidation reaction. So if you have magnetite, you will have an oxidation reaction. So this is how reactions are. So you can take ulvospinel plus plagioclase and you will get a garnet. You will get magnetite plus plagioclase, you will get a garnet. But all these assemblages also occur in the amphibolite phases. They are not classic granulite phases assemblage. These are not classic granulite phases assemblages at all. But these types of reactions are very commonly observed. Okay, I think I will stop here, and we will continue the class in the next lecture.